All right, guys, the goal today is to use trigonometric identities, basic trig identities, which we'll go over, to prove, verify, establish new identities. So everything you're doing is basically a short algebraic proof. It's the algebra. You'll hear me say this over and over. It's the algebra in pre-calculus or calculus or any other math course where the kind of the struggle is. The new material is not generally that bad. All right, let's dive in. All right, so once again, we have these fundamental trig identities, and we're going to be simplifying trigonometric expressions, but I call them proofs. Okay, so as you simplify, you're going to be writing a reason, and you're going to be doing it step by step. So it's really like, it's a proof. You're justifying every step of the way, even when it's as super basic. All right, so just to kind of clarify, an identity is basically any two expressions that you can show are equivalent. Okay, for example, x squared minus y squared is the same as or is equivalent to or equal to x plus y quantity times quantity x minus y. If you were to distribute this out, you would see that it would simplify to x squared minus y squared. Let me write another one. We're going to actually use this one. I'm not going to verify that one, but let me start off with another one. So if I want to do x plus y squared, right? I'm going to actually prove to you really quickly that x plus y quantity squared it's not x squared plus y squared, it's actually x squared plus 2xy plus y squared. And there are memes about this, but basically if you square any binomial, you will always get a trinomial, no matter what, without exception, and it's of the form on the right. So let's do an actual algebraic verification, an algebraic proof that's going to be very similar to the trig proofs. All right, so here's how every single proof needs to begin. You write down the given expression. Okay, so you're basically saying, okay, I'm starting with this. Why? Because it was given. It's just like in those geometric proofs. You have to start somewhere. We're starting with x plus y quantity squared. And then, one step at a time. So the first thing I'm going to do is rewrite it as x plus y times x plus y. Now, why? Because now over here, I'm going to have to give a reason as I do the trig proofs. Here, I would literally, now you're not going to use this particular identity, but you could. That's just the definition of exponent. So you have to give a reason off to the side. You can underline it, you can just write it, you can put it in parentheses, whatever, I don't care, but you have to give a reason. Okay? Then, I can distribute, right? So x times x is x squared. X times y is xy. Y times x is also xy. And then y times y is y squared. Now here's where we can argue what this is called. Now, I call this the distributive property. Dist prop. Okay, so you can underline it, you can put it in parentheses. It's also called the FOIL method. Now just to, I don't know if you've ever seen that term. That's a big deal. I generally don't say FOIL. A lot of teachers will say FOIL it out, FOIL it out. I don't. I say distribute or multiply it out. But just so you know, when you multiply a binomial times a binomial, you're going to multiply 4 times. So you have the first product, then you have the outer product, then you have the inner product, then you have the last product. So when you have a binomial times a binomial, you're foiling it out, meaning you're multiplying it out, you're distributing. People use that even when it's not a binomial times a binomial. So the term FOIL has come to mean in the last 50 years, so it's not that old, has come to mean you're just multiplying it out. So if you were to write FOIL here or multiply there, that's fine. And then the last step is 1xy plus 1xy is 2xy. And then here's where you're going to write this a lot. So you will actually write simplify. You can write combine like terms. You can be very specific, but anytime you're just using a basic algebraic property, or you're combining like terms, or you're multiplying, or you're subtracting, if you just write 1 minus 5 is negative 4, you're just simplifying. Okay, you could say it's a substitution property, meaning there are a lot of reasons. I'm not worried so much about the word that you use for an algebraic justification. I am worried about you knowing the trig identities by name. And today there are really only 3 of those, so that's pretty easy. But the actual proof, every problem you work is going to look like this. Start with what you're given, and then rewrite it. Give a reason, rewrite it, give a reason, until you've verified, justified, established the identity. Okay, so that's what we're going to be doing, all right, and these are the properties you're this is our toolkit. You need to know every time you flip one of these, every time you rewrite sine of theta as 1 over cosecant theta, or more commonly, cosecant of theta is 1 over sine theta, that's a reciprocal identity. And we know these already. Matter of fact, we defined secant in terms of the inverse of cosine. Inverse meaning the multiplicative inverse, where you've inverted the problem. So secant of theta, we know this. Cosecant of theta, we know this. Tangent and cotangent are reciprocals, so we know all these already. So you're going to use these. Every time you reciprocate, every time you rewrite 1 over cosecant theta and replace that with sine theta, the reason is reciprocal identity. Okay, and then we also know the quotient identities. We know that tangent of theta is sine theta over cosine theta. So we're going to go in this direction a lot. Every now and then we'll go in that direction. But anytime we replace one with the other, quotient identity is the reason. Anytime we say that cosine theta over sine theta is cotangent theta, or the other way around, we're going to call that the quotient identity. So those are the two. We're going to use one or both of these in virtually every one of our justifications, verifications, proofs, whatever you want to call it, all the same. Okay. So let's do a couple basic examples. So generally, not always, you're going to be asked, you're going to be given an expression, and you're going to be asked to simplify. So simplify generally means to make it as simple as possible, rewrite it in terms of generally one trig function. Okay, not always, but most of the time. Okay, so in this particular example, you're given an expression and you're actually told, okay, I should be able to show that sine of x times cotangent of x is equal to cosine of x. Okay, so the proof begins like this. You rewrite the given expression. Okay, how do I know this? Well, it was given, so this is my starting point. Now, in general, and this is kind of our first step, this is step one, I generally, and I'm saying generally because I don't always do it, but the vast, overwhelming majority of the time, I rewrite everything in terms of sine and cosine. Okay, so sine of x doesn't change. Cotangent of x is cosine of x over sine of x. And then over here you give the reason. How do I know that? That's one of my quotient IDs. So you can abbreviate quotient ID. So you can abbreviate if you want. You can write out the entire term. You don't have to draw a line. I'm going to draw a line just to draw your attention. You've got to include this. And then here's where a lot of teachers want a lot more detail or a lot less detail. I'm saying this is just simplification. Sine of x times anything over sine of x, the sine of x values, divide out. And this simplifies to cosine of x. And how do I know that? I just simplified. I mean, you can write a lot of different words there. I reduced the fraction, I multiplied, I divided out sine of x, but we simplified. That was algebra. There was no trig involved in that. That was just an algebraic expression that we simplified, and then I always drop my little square. That little square in the math world means end of proof. You absolutely do not need to draw that little square, but it's fun to draw it. And you'll see that in math textbooks if you go into the math world, even in calculus textbooks. When you finish a proof, little square, done. All right, let's try another one. Example 2, an ugly something, 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 and we're going to prove that we can simplify that and get 1. All right, so here it goes. Rewrite it. Sine of x times secant of x times cotangent of x. Once again, rewrite everything in terms of sine and cosine. Put a dot if you want for multiplication so you understand. Secant of x is 1 over cosine of x. Cotangent of x is cosine of x over sine of x. Now, this is where you have to write the reason. Okay? So the first substitution, I just ate some really cold food and my tongue is heavy. It's numb. Okay. So secant of x is 1 over cosine of x. How do I know that? That is the, or one of the, reciprocal IDs. And, okay, so I need to make the line a little bit longer because I'm running off the screen here. And then I also know cotangent of x is cosine of x over sine of x. So I used a reciprocal ID and I used a quotient ID. Okay. So there we go. Got to give a reason. Then, once again, now they're just going to simplify. My cosine of x's cancel. My sine of x's cancel. Right? So at this point, it's just algebra, numeracy, numerical relationships, whatever you want to call it. I know that this just leaves me 1. The reason is, once again, I simplified, reduced, divided out, whatever. Okay, so those are really basic proofs. I'm simplifying, I'm giving a reason as I go. That's just kind of getting us started. Okay, so we've already seen the reciprocal identities. We've already seen the quotient identities. There are a couple more. The major one is what's called the Pythagorean identity. It comes straight, literally straight from the Pythagorean theorem. So let's do a quick, I guess it's a proof, but it's more of just a, here's where it comes from. I don't want you to think it just fell out of the sky. So we know Pythagorean theorem states if I'm given a right triangle. So if the triangle with sides A, B, and C is a right triangle, then the relationship between the sides is a squared plus b squared equals c squared. The converse of the Pythagorean theorem is this. If I have 3 sides of a triangle that have this relationship, then the triangle must be a right triangle. So the Pythagorean theorem begins with a right triangle. Okay, so Pythagorean identity. So here's my triangle. A squared plus b squared equals c squared. I'm going to divide both sides by c squared. Why? Because I can. So this is a squared over c squared plus b squared over c squared equals c squared over c squared is 1. And then I'm going to rewrite this expression a squared over c squared as a over c squared. And if I were to do a over c times a over c, I would get a squared over c squared. So all I'm doing right now is just manipulating the equation. So every one of those equations are just a manipulation of the Pythagorean theorem. Given a right triangle, a squared plus b squared equals c squared. Now here's where the Pythagorean identities come into play. I know if I take just this base angle here, theta, I know, it's going way back, I know what sine of theta is. Sine of theta is opposite over hypotenuse, a over c. You can kind of see where I'm going with this. Cosine of theta adjacent over hypotenuse B over C. So I make a substitution. I replace A over C with sine of theta. So I have sine of theta squared plus, and then B over C, I can replace B over C with cosine theta squared equals 1. And then that's generally not how you write a trig function squared. So we've seen this before. Instead of writing sine of theta quantity squared, we write sine squared theta. Those mean the same thing. Different ways of writing this. The history of that, I used to know the history. I used to know when that shifted, why that shifted. But you can Wikipedia that, Google. Why sine squared of theta? Siri! Okay, we'll ask her later. Oh man, I just activated like 12 phones in this house. Okay. So, it's called, just to be silly, guys, you know, we're not in the classroom, but we got to keep it fun. This is the OG Pythagorean ID. That's my $1 million rhyme. OG Pythagorean ID. It's the original. Okay, so the Pythagorean identity is sine squared of theta plus cosine squared theta equals 1, and it literally falls straight out of the Pythagorean theorem. So all we've used is the Pythagorean theorem and the definition of sine and cosine. Okay, now, but that's not the only Pythagorean identity. That's the most common. The others are, okay, so easy to generate. So we're going to generate 9 variations of the Pythagorean identity, and just so you're not freaking out like 9, that's crazy. It is crazy. But every time you see a squared trig value in an identity problem, you're ultimately somewhere in that problem going to use Pythagorean identity. So just know, every time you see tangent squared, secant squared, sine squared, cosecant squared, whatever, you're going to ultimately make one of these substitutions. So you'll use them so often that they're not that hard to memorize. So we have the OG and the OG. That's the original. I'm going to take each one. I'm going to divide both sides by sine squared theta, sine squared theta. So sine squared theta divided by sine squared theta is 1. Cosine squared theta over sine squared theta. Now we know that cosine over sine is cotangent. So if I have cosine squared theta over sine squared theta, that is cotangent squared theta. 1 over sine squared theta, if I reciprocate both of those, so that's sine of theta times sine of theta, 1 over sine squared theta is cosecant squared theta. So this is another Pythagorean identity. Where did it come from? It came from the OG, where you divide everything by sine squared theta. Okay, so you have variation 1, variation 2, and then variation 3 is where you, instead of dividing by sine squared theta, you divide by cosine squared theta. And once again, if you're wondering, why do we have to do all these variations, you'll see in a minute. As we start doing all of these verifications, you'll see all of these different versions kind of pop up in the problem. So it's just nice to have seen each of these manipulations before you just dive into the problems. So sine over cosine is tangent, so we have sine over cosine, sine over cosine. So this is tangent squared of theta plus any number divided by itself is 1. 1 over cosine squared theta, secant squared theta. That's my third iteration. So if you take OG, divide by sine squared theta, you get a relationship between cotangent and cosecant, all right, squared. And then if you divide the OG by cosine squared, you get a relationship between tangent squared theta and secant squared theta. And really, you can swap that around. So if you see tangent squared theta plus 1, or if you see 1 plus tangent squared theta, you can replace that with secant squared theta, or the other way around. If I see secant squared theta in a problem, I can replace it with tangent squared theta plus 1. So that's true for both of these. All right, so we have three basic iterations or ways of representing the Pythagorean identities. But for each one of those, we could tweak it. So I'm going to show you, generally you don't see this. You will see this. You will just see sine squared theta plus cosine squared of theta, and you can replace that with 1. And that will happen sometimes. But honestly, more often what you see is if I take both sides of this equation and subtract sine squared theta, then I'm going to get this version. This also is one of the Pythagorean identities. So in a problem, if I replace 1 minus sine squared of theta with cosine squared theta, the reason is going to be Pythagorean identity. Okay, and another variation, if I take both sides of OG and I subtract cosine squared theta, I'll get sine squared of theta equals, I'm subtracting cosine squared theta from both sides, so this becomes 1 minus cosine squared theta. So we have, for OG, we have 3 common variations. We're going to see all 3 of these in this video and certainly in the next video, and as you work problems, you will see that a lot of different times. Okay, same here. If I take both sides of this equation and I subtract 1, minus 1, then I get tangent squared of theta equals secant squared theta minus 1. So this is another iteration. So if I see anywhere in the problem, if I see secant squared of theta minus 1, I can replace that with tangent squared theta. Reason? Pythagorean identity. We're going to see that today. Okay, and then, or I can actually, what's the other little, I can subtract tangent squared theta. So if I subtract tangent squared theta from both sides, I'm left with just 1, and I'm left with secant squared of theta minus tangent squared theta. And this one's not very common, but you might see it. So if somewhere today or tomorrow or next week you see secant squared theta minus tangent squared theta in a problem, you can replace it with 1. Okay, so that's 3 variations of tangent squared, secant squared. Okay, remember, if you forget this one, you can always go back to the OG, divide, and regenerate it. So the only one I've memorized to this day, I'm just being honest, y'all, I've memorized OG, and every now and then I have to kind of remind myself, is it plus 1 to tangent or is it minus 1? And I just have to, you know, I don't like to memorize a lot of stuff. I like to kind of understand where it comes from. And over time, you just commit it to memory. Okay, same thing here. I can take this equation. I can subtract 1 from both sides. So another iteration, another variation on the original. If you subtract 1 from both sides, then cotangent squared of theta will equal cosecant squared of theta minus 1. So you could replace this expression with that, Pythagorean identity, or 1 equals, and you can subtract cotangent squared on both sides. So cosecant squared theta minus cotangent squared theta. So there are, in all its glory, these are 9 Pythagorean that's an N, identities. Now, once again, there's really only one. Every one of these can every one of these other 8 can easily, in 1 or maybe 2 steps at most, 2 steps at most, guys, you can either divide and move one term to the other side, or you can just move one term to the other side. So every one of these relationships here, you're going to use over and over and over, and they all come straight from the Pythagorean theorem. So these are your Pythagorean identities. Okay, so you have your reciprocals, you have your quotients, you have your Pythagoreans. Pythagoreans mean you have squares involved. So anytime you see something squared, trig function squared, Pythagorean identities will be involved. Okay, then you have this even odd identity stuff that we've seen before. You're not going to use these very often, but every once in a blue moon, if you see, this is generally what you're going to see, if you see cosine of negative x somewhere in an identity, well, you're just going to replace that with cosine of x. Why? Cosine of negative a is the same as cosine of a because those are even. So let me just remind you, going back. These two functions, cosine and its reciprocal, secant, those are even functions. So if you plug opposites in, you get the same number out. All the others, sine of negative a is going to be the opposite of sine of a. Cotangent of negative a is going to be the opposite of cotangent of a, and so on. All the others are odd functions, meaning opposites in, you get opposites out. Okay, so these are called opposite angle identities. They're also called even identities, odd identities. So, for example, if in a problem you see sine of negative x, then you could replace that with the opposite of sine of x, or negative sine of x, and then the reason would be either opposite angle identity. I would say it's an odd function identity. So odd identity, or you can say opposite angle identity. Okay? Once again, different textbooks, different authors, different Khan Academy videos, whatever. Different, they call these things different. They're not standard necessarily. Okay. So here's the game today. You have all the tools you need. You know a little bit of algebra, you know how to factor, you know how to combine like terms, you know how to do all that. You have all the identities by name. So now it's all about algebraic techniques. Okay? You're going to be making a lot of substitutions. That's the easy part. Replacing one expression for another. You will be distributing. Lots of mistakes happen there. It's the algebra, y'all. You will be factoring a lot. That gets people. You will be adding or subtracting fractions. Okay? So this right here is where you want to be careful. That's where most of the mistakes happen. The substitutions using the trig identities, not a problem. All right, so we're just going to dive into some examples. So I've given you all the information you need. Now we're going to crank through a bunch of examples so you can see what the expectation is as you do these problems. All right, so let's dive into our first example. So we start with rewriting. Okay, now when I see this problem, I notice that both terms I'm adding, both terms have a sine of x factor. I'm going to factor out the sine of x. Just because I know that if I factor first, something might clean up. Not always, but generally that's the case. Okay, so here's all I did. Both terms I was adding or subtracting. Both terms had a sine of x factor. I factored out sine of x. Sine of x times 1 is sine of x. Sine of x times cotangent squared of x is sine of x cotangent squared of x. This is the distributive property. So the reason is distributive property. Now, you can write factored. That's fine. You factored. But anytime you multiply something out using the distributive property or factor it out, it's still the distributive property. Now, here's where, if you rewrite cotangent in terms of sine and cosine, you can do that. It's just going to be a longer proof. You'll still get to the end. But I know that this is a Pythagorean identity. So I'm going to use my first substitution using the Pythagorean identity. So I'm going to go back to that long list. And I know, where is it? There it is. 1 plus cotangent squared of something equals cosecant squared of something. So let's go back. So 1 plus cotangent squared of x is cosecant squared of x. Why? That is one of my Pythagorean identities. Okay? Now I'm going to write cosecant in terms of sine. So cosecant squared of x is 1 over sine squared of x. How do I know that? That is one of my reciprocal IDs. Okay? Here's where you don't have to show, you can go straight to the answer, but I know I'm going to go ahead and multiply this out. I'm going to add in an additional step. All right, this is going to be 1 over sine of x. So if you went straight from here to here, the reason would be the same. Simplify. All I did was simplify here. All I did was simplify here. Okay? So you can simplify. You have sine of x understood to be in the numerator. You have sine squared of x here. One of the sine of x's cancels out or divides out, and we're left with sine of x on the bottom. 1 over sine of x is not considered simplified, so we need to make one more substitution. 1 over sine of x is cosecant of x. How do I know that? Reciprocal ID again. And I am done with my proof. So in general, not always, but in general, when you're asked to simply simplify, like that's it, just simplify, then you're going to end up with one trig function in simplest form. Okay? All right, let's try another example. We're just going to crank through several of these, and you'll see the entire bag of tricks before it's all said and done. So, first step, write down the problem. Okay, 1 plus tangent squared of x over cosecant squared of x. I see 1 plus tangent squared of x. I'm going to make a substitution. That is secant squared of x. How do I know? That's one of my Pythagorean. Sometimes I abbreviate, sometimes I don't. Pythagorean ends with an N. Theorem ends in an M. Pythagorean identity. Okay, so that was my first substitution. Then I'm going to actually simplify. I'm going to split this fraction apart. You do not have to do this, but I do want to show you that this is what we're looking at. Okay, we're looking at secant squared of x times 1 over cosecant squared of x. Why is that true? I've just factored it. All right, anytime you rewrite something. Now, I'm only doing this just to kind of show you one time what's going on here. Secant squared of x is 1 over cosine squared of x. 1 over cosecant squared of x is sine squared of x. Okay, how do I know all of that? Those are both reciprocal IDs. Okay, which takes us to fraction times fraction, sine squared of x over cosine squared of x. How do I know this? All I did was simplify. Now, I will never do that again. If you want to go, moving forward, if you want to go straight from here to here, so if secant squared of x winds up cosine squared of x, numerator, denominator, cosecant squared of x is in the denominator and it winds up in the numerator, you have simply used the reciprocal identity. Okay? And then sine over cosine is tangent, so this is tangent squared of x. How do I know that? That is one of my quotient IDs. Now, let me show you this one time. I did have a professor who was crazy. Sine squared of x, we would have to rewrite that as sine of x times sine of x. Cosecant squared of x, we would have to write that as cosine of x times cosine of x. We would then have to split the fractions. And then we would have to rewrite it as tangent of x times tangent of x, and then we would get here. You don't have to do all that, but I do want to show you this is what's going on. So you can go straight from sine squared of x over cosine squared of x to tangent squared of x. That's fine, but this is just a justification. So once again, I'm showing you why things are what they are. You can use anytime you flip, anytime you invert the position of a trig function and rewrite it as its reciprocal, you're using a reciprocal ID. So you could have done this problem and rewrite it, make your Pythagorean ID substitution, use the reciprocal, and then use the quotient. So this could have been Pythagorean, reciprocal, quotient. Done. And then this is as simple as it gets. Tangent squared of x, there's nothing simpler than that in this particular case. All right, example 5. So now every time we do one, we're getting a little bit better, a little bit faster. So I'm going to rewrite sine cubed of x plus sine of x times cosine squared of x equals, once again, I see a sine, I see 3 factors of sine, and I see another factor of sine. I'm going to factor out sine of x. How do I know that? That is the distributive property. Once again, you can say factored, that's fine. So I factored out sine of x. So sine of x times sine squared of x is sine cubed of x. I'm just doing a quick check. Yes. Now, once again, I've seen students do this proof and they've gone all over the world. 8 steps later, they get the answer perfectly okay. But this is my OG. So this is sine of x times sine squared of x plus cosine squared of x is 1. How do I know? OG Pythagorean ID. Hey! So sine of x times 1 is sine of x. How do I know that? I just simplified. And then once again, I'm back to putting my little boxes that I haven't done in a minute. You can put it or not. I just like to do it. So I have simplified this expression completely into one trig function. All right. Next, example 6. Okay, so now we're going to get a little heavy in the algebra. All right, so I'll rewrite the problem. Secant of x plus 1 times secant of x minus 1 all over sine squared of x. Now, I'm going to use an identity. Anytime you have a binomial times what's called its conjugate, you can FOIL this out, distribute it out, and it will be secant of x times secant of x, which is, of course, secant squared of x. Outside, negative secant x. Inside, positive secant x. The middle terms cancel back to 1 times negative 1 is negative 1. So how do I know this is true? That was just, we can call this distributive property. We can call this simplifying. We can call this foiling. I'm going to call it the distributive property. You can call it FOIL. FOIL. So it's completely up to you what you call that. Okay, but when you multiply this binomial times this binomial, you will get a binomial. Okay, and if you go back to the very first identity we talked about that I didn't verify, that I just, so that's it. All right, so then we're going to use the Pythagorean. I know secant squared of x minus 1. If you look on the front of your notes, secant squared of x minus 1 is tangent squared of x over sine squared of x. How do I know? That is the Pythagorean ID. I'm going to move this over just so I have more space. Now, I'm going to split the fraction. You do not have to split the fraction, but to me that makes it so much easier to manage. So I know that tangent squared of x over sine squared of x can be split. All I did was factor. It's not simplifying. It's actually the opposite of simplifying. That's no different than if I take the number 10 and I rewrite it as 2 times 5. Well, how do I know that? I just factored it. Same thing here. I rewrote one number, even though it's a fraction, it's one numerical expression as a product of two. That is factoring. Okay, now tangent squared of x. Oh, I'm sorry. Scoop. Now I'm going to rewrite tangent squared of x in terms of sine and cosine. Now, just in case you're wondering, why didn't I do that up here? Because then I would have had a fraction in a fraction, which is fine. It just looks messy. So I generally do not rewrite secant squared or tangent squared or any other function in terms of a fraction if I already have a fraction. Okay? So how do I know this? That's one of my quotient IDs. And then my sine squareds divide out, and I'm left with 1 over cosine squared of x. All I did was simplify. And then I can rewrite this as secant squared of x, and that is my one of my reciprocal IDs. End of proof. So all of this ugly expression simplifies to secant squared of x. Put my little box and shade, meaning done. All right, guys. Hopefully you're starting to see the pattern. We'll knock a couple more out. Into the next. So rewrite it. Cosecant of x minus cosine of x times cotangent of x. Now, in this problem, I don't see anything I can factor out. And there's not already a fraction. So I'm going to rewrite everything in terms of sine and cosine. Hopefully that'll clean up nicely. Maybe not. So cosecant of x is 1 over sine of x minus cosine of x, leave that alone. Cotangent of x, I'm going to rewrite as cosine of x over sine of x. So I've used two identities in this case. I used a reciprocal identity, and I used a quotient ID. So I used one of the quotient identities. Now, I'm going to go ahead and simplify that a little bit. So 1 over sine of x minus cosine of x times cosine of x is cosine squared of x over sine of x. Now, once again, this is where knowing how fractions work becomes really important. All I did was simplify. You can write algebra. You can write, we already know this. You can write elementary school. You can be funny with this. You didn't use one of your trig identities. That is just strictly algebra. Then these two fractions are being added or subtracted, and I have a common denominator. So I can rewrite this as like that. So it's no different than if I have 1 over 7, or let's say, let's make that 4 over 7 minus 1 over 7. Well, that's just 4 minus 1, which is 3 over 7. So when you see this and you have a common denominator, you can combine, no different here. So 1 minus cosine squared of x all over sine of x. How do I know that? Simplify. Okay, that's just subtracting two fractions with a common denominator. If you want to write all that, you can. Now I kind of see where I'm going with this. 1 minus cosine squared of x is sine squared of x. That's one of my manipulations of my OG, but it's not the OG. So that's one of my Pythagorean IDs. Then you can simplify it just to kind of make this clear. I haven't made it clear in the past, but that's sine of x times sine of x all over sine of x. That's what this means. So one of them cancels, and I'm left with just sine of x. How do I know? I just simplified. Done. End of proof. So we took cosecant of x minus cosine of x times cotangent of x, and we manipulated until we simplified it all the way. All right, let's look at one last example. All right, so let's rewrite tangent of x times sine of x plus cotangent of x times cosine of x. Okay. Now, if I distribute out the tangent of x, that's going to be crazy. There's nothing to factor out here, so let's just rewrite everything in terms of sine and cosine, see what happens. Tangent of x is sine of x over cosine of x. Leave sine of x alone, plus cotangent of x is cosine of x over sine of x times cosine of x. So this was, they were both, we used both of our quotient identities. Okay, now let's see what happens. Let's leave a little space. Okay, let's clean this up a little bit. Sine of x over cosine of x sine of x plus cosine squared of x over sine of x. All right, all I did was simplify. Now I see I have sine of x as a denominator here, so I'm going to actually rewrite. Once again, at this point, it's just all algebra. I'm going to rewrite sine of x as sine squared of x over sine of x. I'm going to build a fraction with a common denominator. I can start to kind of see where I'm going here. So how do I know that's true? I just built. Now, I'm going to say this. You can write algebra, numbers, whatever. But you need to give a reason. You need to stop and make sense of this. I'm going to write least common denominator, or you can say common denominator. All I did was build. I have a denominator of sine of x. I built another fraction that had sine of x in the denominator. So what I did was I, in essence, multiplied top and bottom, numerator and denominator of this fraction by sine of x over sine of x. Okay? So now, still haven't done anything with this term in front. It's just originally I'm just dragging it along. Now I'm going to combine like terms. I'm going to add the two fractions. Sine squared of x plus cosine squared of x all over sine of x. How do I know? I simplified. Just added the two fractions. Now, OG time. So sine of x over cosine of x. Sine squared plus cosine squared is 1. How do I know that? That's my OG Pythagorean idea. Then, last step, running out of space. You guys are so much neater than I am. Thank you. 1 over cosine of x. How do I know? I just simplify. And then my last step, 1 over cosine of x is secant of x. How do I know that? That is one of the reciprocal IDs. And proof, if we were in the classroom, this would look so much nicer. Using these PowerPoints, I need to find a better way, but that's all right, we'll get there. Guys, that is 8 good examples of what it means to basically you're proving trigonometric identities. Just know that when you simplify, if you're asked to simplify an algebraic expression, you're writing a proof, you're verifying something, you're really establishing a new identity. So let me go back to the bottom. You've just proven that this original expression, all that actually is equal to secant of x, which will take us into our next video, really our next two videos, where you'll be given an identity and you're asked to prove the identity, to establish it or verify it. So every one of these problems will ultimately look the same. Start with one expression and then manipulate that one expression until it looks like something else, and that's the proof. All right, guys, it was a long one. The next one won't be as long because we're just going to dive into some more complex problems and learn, kind of add to our bag of tricks. Everything at this point really will be, for the most part, just new algebraic tricks. All right, so have at it, guys. Work those practice problems. There are a lot of them, so I can't stress this enough. The more you do this, the fewer the steps you'll use as you go through the process. So you'll go from 12 steps or 9 steps to maybe 4 or 5, and your proofs will get cleaner and cleaner, and you'll get less frustrated. So this isn't something you can cram. You have to work a little bit each day or every couple days. So just get on this, work it out. You got this. And all right, I will see y'all in class.